Okay, so good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. This afternoon, we are really privileged to have Professor Guy Midgley as a speaker. Guy is a world-leading expert in the fields of global change and biodiversity, and he's worked in that area since the 80s, first at the South African National Biodiversity Institute, and later from 2014 as a professor of botany and zoology at Stellenbosch University. Yeah. He's an NRF A-rated researcher with hundreds of publications, a highly cited researcher according to most databases of publication. He was recently awarded the Marlot Medal of the South African Royal Society and the Humboldt Foundation Research Award for Lifetime Science Contribution. So, Guy, we are really very happy that you accepted the invitation to share with us some of your wisdom around climate change and related topics. Yeah, and you already started sharing your screen, so please, over to you. And maybe just a quick reminder to the participants to use the Q&A to ask questions, and maybe towards the end you can raise your hand virtually, and we will give you the right to ask questions in person. Guy, please.
Thanks, Francesco, and I'll try and finish within about 35 minutes to give plenty of time for discussion. I know people are probably pretty worn out at this stage of the year, so it's not. I'm not going to push your attention span for too long. But I'm very happy to have this opportunity to share this idea. And it's not an idea that's unique to me, but it's been brewing in a number of different forums, as I'll show in the talk, and it relates to this concept of where is the sweet spot for modern civilization when it comes to climate and atmospheric CO2. And as you all well know, at COP27 and in the UNFCCC, the Framework Convention for Climate Change, lots of discussion around this topic. And, the discussion is informed very much by, I think, an ahistorical concept of how human civilization, atmospheric CO2 and climate have interacted. And I find it extremely interesting to go back into deep time, into the history of the human species, evolutionary history, to explore this idea in a little bit more detail, because I think it adds a lot of value to our perception of where we should be trying to aim with regard to climate policy. And I think some interesting it creates some interesting questions and some ideas. This landscape, a few people were asking, is in the vicinity of Prieska in the Northern Cape. And what you see in front of you is the imminent clash of two biomes as CO2 rises and as climate warms and rainfall seasonality shifts. The C4 grasses, warm season grasses, become more common in these sorts of areas, and with them introduce a fire regime which may well start to threaten the succulent plants which are marching eastwards at the same time. So these are interesting clashes of biomes that seem to be entering our landscape. But anyway, that's beside the point. I want to talk about the deep time aspect. I start off with the deep time aspect of CO2 and human society. So thanks, Francesco, for inviting me, and thanks all for listening. Let's oh, sorry, I've got two computers in front of me. Let's start with this slide. And as it says in my abstract, this is really what poses the question. We know that the evolutionary history of Homo sapiens is probably 150, maybe 250,000 years. we see possibly a little bit older. I mean, it depends on where you are on this on the spectrum of the emergence of Homo sapiens, or your belief in the emergence of Homo sapiens. But what you see in front of you is a slide that shows the temperature with respect to current day conditions, which is this dotted line, going back about 500,000 years. This is from ice core data, which are derived by scientists in the 1980s and 90s, who found that you could sink these ice cores into the Greenland ice cap and the Antarctic ice cap, and go down more than 1 kilometer in depth, and you draw back ice which has captured bubbles of air which were formed hundreds of thousands, tens to hundreds of thousands of years ago. And it's an incredible record of our atmospheric CO2 and temperature history, because as you melt these ice cores, you can date them and you can extract the CO2 concentration from the atmosphere that was formed at the time that snow fell. And because these ice cores are so thick, it captures very, very ancient atmospheres, almost up to 1 million years now. We've got some cores going back almost 1 million years. And so from extracting those data, we can see that the temperature of our planet over the last 500,000 years has really fluctuated from its current sort of warm interglacial state, which is represented here. So that's the current condition, and to very cold conditions about 18,000 years ago, 23,000 to 18,000 years ago, a period known as the last glacial maximum, the LGM. And this was, the whole planet was about 5 degrees or a little bit cooler than was the case even before we started to burn fossil fuels. And you can see that in general, this is a period called an epoch called the Pleistocene, and it began about 1.8 million years ago. And for much of that time, about 80% of that time, the planet has been about 5 degrees and more cooler than we even had before we started burning fossil fuels, with these occasional excursions called interglacials or interstadials, which last a few thousand years, maybe up to 10,000 years, where the world warms up sporadically and then cools back down again. And it's a bit like a heartbeat. You see that the planet cools down to a certain point, and then warms up again. But it's bounded. It's bounded between these two limits. And there's a lot of work that's been done on understanding exactly why the world would top out at a certain temperature and not get any warmer, and bottom out at a certain temperature and not get any colder. And it really relates to the carbon dioxide, the carbon cycle, which reaches a cold point. And it's thought that CO2 limitations, particularly relating to plants and tree roots that cause weathering, slow down because those plants become carbon limited. And that's what sets the lower limit. So in other words, plants cannot drag any more CO2 out of the atmosphere than at that point, and the world cannot get any cooler. And then when the world warms through natural variations in the orbit of the planet, which kick off a process that results in a feedback between warming from the sun and the feedback from the carbon cycle, things warm up very rapidly. The oceans start to degas carbon dioxide, and there's a kind of a feedback effect. The planet warms naturally, and then it slows down again, and vegetation switches back on, starts to suck CO2 back out of the atmosphere, and there's a very strong feedback, particularly from terrestrial vegetation, which prevents a runaway warming. And that sort of pulse has been going on for about 500,000 years. It does extend all the way back to 1.8 million years ago. It gets a little bit more chaotic a little bit further back, but this is the last 500,000 years. And this is this is really our species was born in this age, in the Ice Age. We are born of the Ice Age. And there are all sorts of things that happen to the planetary ecosystem when CO2 is low and when the temperatures are cold and when the world is dry. But the most important thing to point out is that these little blips, these warm blips, are a minority of the time. And we see these as, this is what the world looks like. In fact, not at all. We live on a planet that for almost 2 million years has become much more adapted to much colder, drier, and less productive conditions. Low CO2 limits plant growth, limits plant productivity. And this is the atmosphere in which modern humans emerged. And our lifestyles would have been shaped more by a low CO2, low productivity world than by the world that we currently live in. So that's a really important thing to point out, and we need to, I think we need to really take that on board as we understand our place in the world and where we want to be aiming with respect to climate policy. I'm now showing you, a lot of the work on human history has focused very much on human lifestyles during this period, has focused on the role of climate, the temperature, the dryness of the climate, which paleoanthropologists have used to explain human history and human development, including diet, the human diet, but also human behavior. And one thing that's very often left out, in fact, almost always left out, is the fact that carbon dioxide levels would also have played an important role in the way that humans would have been able to utilize their environment. Because under low CO2 levels, plants are much less productive. They're limited by carbon. They have strong limitations on how much fruit they can produce. Bulbous plants are limited with respect to how much carbon they can store in those bulbs, and these are things that humans would have been utilizing, right, in their history. And if you look at the period of human history, the vast majority of it has been in these very low production, low productivity landscapes with limited carbohydrate availability. And it's interesting to speculate that the macro element, the macronutrient that we produce ourselves is carbohydrate through gluconeogenesis. We don't need to eat carbohydrates. The other macro nutrients we have to eat, protein and fat, but carbohydrate we produce ourselves. And that's a pretty interesting observation given this long-term history. But you'll see if you listen to paleoanthropological talks, and there are quite a few up on YouTube which are fascinating, is they always talk about coldness, ice, dryness. They never talk about CO2. And for me, this is a huge missing element of understanding human history and human evolution. What did the world look like during these low CO2 periods? Well, if you reconstruct the pattern of global biomes, you'll see that it's radically different. This is a reconstruction based off of pollen data, and it's somewhat confirmed by modeling using these what are called dynamic vegetation models, global dynamic vegetation models, PGVMs. And you can see that during these low CO2 periods, when the world was cold and dry, for example, at the LGM here, the tropical forests of the planet contracted substantively. And it's been shown by some modeling groups, for example, Harrison et al., Prentice, that you can't really explain the contraction of tropical forests purely using climate, using temperature and drought. You have to invoke the low CO2 effect and its depressive effect on plant production. So these ecosystems are highly carbon limited, and it's fascinating to speculate what people were forced to do. I mean, you'd have to be forced to hunt, which is a dangerous activity, and it's far preferable for people to gather. Much more dangerous to hunt, and this would have been necessitated by a general lack of carbohydrate in their environment. One of the few sources of carbohydrate, well, a couple in plants, sugarcane, for example, and possibly maize, but we've bred maize to be much more productive than it used to be. But one of the carbohydrate sources would have been honey, and honey would have been an extraordinarily carbon-rich source at these times. So it's no surprise that bees are almost suicidal, or they are suicidal in the defense of the honey in their hives. That would have been very strongly selected. Francesco's died. Is everybody else still on? Is everybody else still online? I don't even know how to tell. Can somebody give me a thumbs up? Oh yeah, no, okay, so we seem to be online. Okay, Francesca will not join us. Okay, thanks for the thumbs up. All right, so isn't it fascinating okay, Francesca, I see you again, that this aspect of human history, deep history, has been virtually ignored. I mean, think about things like the honey guide, which evolved as a strategy to guide primates to honey in this special group of African birds, clearly highly selected by the extreme rarity of carbohydrate in the environment. But if you look at how do plants do under low CO2? Is it such a big issue? Well, there's been quite a lot of experiments done, and I'm not showing some pictures of our own work, which shows how tree saplings are enormously limited by low CO2. But I thought this little picture of this little herbaceous plant, Butylon theophrasti, grown under glacial CO2, under pre-industrial CO2 current, and in future CO2 levels, or potential future CO2 levels, hopefully we won't get to 700 parts per million, but shows how under glacial CO2 levels, the growth rates of herbaceous plants were significantly restricted. And if you look at the production of wheat yields, so this is modern wheat, not the ancient variety, but you're pushing CO2 back to glacial levels below 250 ppm. We can see that the yields of wheat are very, very substantively reduced. But by contrast, would mean that as CO2 rose at the end of the Pleistocene, the production of cereal plants would have increased substantively. And indeed, what we see at the end of the last glacial maximum, I'm switching timescales here to the last 12,000 years now. This is not millions of years anymore. We came out of the LGM 18,000 years ago. The world started to warm, CO2 started to rise, and this is one of the reconstructions by Market et al. Of the likely, the best fit temperature curve for the Holocene, which started about 9,000 years ago. And you find that human agriculture starts to really kick off. The early signs of human agriculture start to kick off a little bit before this, but they're really the strong signs of human agriculture start to show from about 12,000 to 10,000 years ago. And there's a lot of work now that shows that this is the case. There are signs of early humans, Stone Age humans, using primitive crop types. You can see it in residue on stone tools, but it's very, very limited until about 12,000 years ago. And then so it's almost as if humans were poised to start using these crops and to settle down and to avoid the need to hunt and rather to farm. But it was only once CO2 rose to above about 250 parts per million that you see the widespread use of these cutting tools that are thought to have been used to harvest the cereal plants. So this really starts to take off in the Levant and a whole range of regions in the Middle East and Southern Europe and North Africa and Asia. And we see the evolution of intensive cultivation kicking off only once CO2 has risen, temperatures have warmed, and the world has become a more productive place. And I think it's wildly underappreciated that why did it take so long? If humans were on the planet for 100,000, 150,000 years or more as a modern species, why on earth did it take so long for us to become a sophisticated, settled farming species? And I think a lot of the answer lies in the CO2 and combined climate change impact. And here's some really, really beautiful work done by Maida et al. Published in quaternary science reviews, showing the rise of use of sickle blades in different parts of the world and in the percentage of cereals that starts to emerge in the human diet. It's our use of intensive agriculture is really very, very recent in our evolutionary history. And that again is to do with this yield curve of C3 plants of cereal crops to CO2, and we can see how heavily limited they were and finally became released from the CO2 effect. And we can see projecting into the future that, and we have seen increases in crop production in response to rising CO2. We've also seen increases in the production of woody plants and natural ecosystems in response to rising CO2, which have in fact saved us from quite a considerable proportion of the global warming that would have happened had this effect not been in place. And I'll demonstrate that to you in a slide right towards the end of the talk. It's not a very long talk. I'm about halfway through already. So it's not only C3 plants or these plants that are highly sensitive to CO2 that respond to rising CO2. It's also the C4 plants, or the plants that have evolved a mechanism to perform very well at low CO2 level, also show a strong temperature optimum, which frees them from the restrictions of a cooler, drier climate, and really allows agriculture to take off, and has allowed us to breed maize and other crops to become much more productive. And we've been selecting plants, taming plants to become in service of human populations ever since then. In fact, taming a whole ecosystem, not only plants, but also animals. And we now have tamed much of the planet and farm much of the planet as a consequence of all this, and our whole economy. The evolution of money, the evolution of value, it relates to the production of excess food and then the evolution of modern society. Not possible before CO2 rose and temperatures warmed. The question then becomes, what's the sweet spot for modern society? We can start to explore this by looking at how there was a thermal optimum during the Holocene between 8,000 and 6,000 years ago. Interestingly enough, this is a time where there was a green Sahara in place. You're not quite sure if that relates to rising CO2 or some particular orientation of the radiation input, ocean temperatures, and broad circulation patterns. But since the Holocene thermal optimum, we were on a downtrend towards the next glacial, as you can see. And by chance, we figured out that we could burn fossil fuel. And that has radically turned around what would have been a natural decline into the glacial, maybe a few thousand years hence, as has happened traditionally over the last 500,000 years. And we turned that around through burning fossil fuels. But, and this is the Goldilocks, the Goldilocks molecule. We've released this molecule from its stored state back into the active biosphere. And this has warmed the world. Up until about 2014, I think some of you will remember a big debate between 2000 and 2012, where a lot of climate skeptics said that the warming had paused and that CO2 didn't cause warming, but sadly they've now had to eat some humble pie, because warming has continued relatively unabated, with some natural fluctuations. We're now sitting well above 1 degree. And now the question is, what's the safe space for modern human society? And we've saved ourselves from a glacial, but are we threatening to move out of the sweet spot for modern human society and destroy this optimum zone? There's no doubt that one of the things that is preventing a more rapid rise in the risk to ourselves is the fact that natural ecosystems have been absorbing roughly 50%, or maybe even more, 60% of our emissions for several decades now. And this is shown, and I really wanted to show this to you in this graph, which balances emissions and the sinks, sources and sinks of CO2. Of course, these two have to be a mirror image of each other, because they balance each other perfectly. And you can see that emissions from fossil sources and from land use change on the top here are balanced by the sinks. Where does the carbon go? And interestingly enough, only a proportion ends up in the atmosphere, causing rising CO2 levels. But quite a chunk, about 25 to 30%, it's a bit variable depending on annual variability in climate, goes onto the land surface. It fertilizes the growth of plants and is captured and ends up in the soil or elsewhere, maybe even in exudates, and then ends up in the oceans. And then a chunk of it, about 30%, ends up acidifying the oceans. It's absorbed directly into the surface of the oceans and causes a reduction in the pH of oceans. So those two processes have prevented even faster warming. But the ocean acidification isn't ideal, and the impacts on natural ecosystems may also not be ideal. They may be causing risks to some ecosystems as well. But certainly, we need to look after our ecosystems to make sure that these services do not become weakened by further warming. And there is some evidence that under further warming, this particularly the terrestrial sink may become weaker as the world becomes too warm, and this may turn into a source and causing an acceleration of warming. So once you look at these deeper time factors, you start to understand how vulnerable we are. And if we don't get warming under control, as has been shown by IPCC, we can end up with some really adverse effects on temperature and on rainfall change. So the drying of winter rainfall zones is one of the best predicted or most commonly predicted impacts of this kind of climate change. So what is the sweet spot for human civilization, and what is the risk to us? This has been looked at in a fairly recent paper, and I'm afraid I've just noticed I've omitted the reference here. But if you Google the potential niche space for modern society, I think you'll pick this one up. It was published, I think, about 2 or 3 years ago. And what these authors did was to model the potential climate space available for human society in terms of mean annual rainfall on the x-axis, mean annual precipitation, I should say, on the x-axis, and mean annual temperature. And this point cloud shows you the density of pixels on the planet that occupy, this matrix of rainfall and temperature. And you can see that, quite a large chunk of the planet is quite dry and cool, and there's a chunk that's dry and warm, and then this little leg here where it gets really, really wet and warm in the tropics. So tropics, temperate ecosystems, and then the polar regions down here. Interestingly enough, human society seems to be caught between two competing drivers on this axis. So if we plot onto the same set of axes soil fertility and net primary production, we can see that NPP, which is driven primarily by CO2, but also by temperature and rainfall, is concentrated here in the tropical areas. But soil fertility is highest where rainfall is lower and it's a little bit cooler, so where there's less leaching of nutrients out of the soil. So these two contrasting things mean that if you want to have a highly productive agricultural system in this space here, you need to fertilize because the naturally rich soils are suboptimal, or you've got to irrigate in these areas, or you've got to fertilize these areas. And that is the story of modern agriculture, irrigation and fertilization. Because the human niche sits somewhere between those two limits to productivity, nutrition, soil nutrition, soil nutrient status, and climate. So going back to 6,000 years ago, 500 years ago, and now, this paper looked at the human niche and found that it's remarkably constant at in this sort of climate space, around about 1,000 millimeters of rainfall, a little bit lower, and between 10 and 20 degrees mean annual temperature. That's where human society tends to congregate, and it's somewhat aligned with where our crops grow, where our livestock is found, and interestingly enough, GDP is positioned a little bit wetter, and indicates to me that the richer part of the world, the wetter part of the world in the Northern Hemisphere, is probably exporting a lot of food and production to enable GDP to be a little bit higher in a suboptimal area of the human niche. But I just show this to you as a really interesting analysis of us as a modern species and the constraints to our modern society. Now, where do we go from here? This is my last 2 slides. Well, we just come out of the Conference of the Parties at the Framework Convention on Climate Change, and we see that some countries are already starting to emphasize the need to stay close to 1.5 degrees and to radically reduce our fossil fuel use. Particularly, interestingly enough, some developed countries like the European Union and the US, Canada, and others are starting to really push for rapid decarbonization, I suspect because they have seen some pretty adverse effects of climate change in their own countries in the last year or two, and have suddenly woken up to the real risks which have traditionally been borne by the developing world. And so now We see strong calls for decarbonization by the developed world. What's likely to happen? Well, we could follow some sort of decarbonization path, which will lead to a topping out of warming and hopefully some kind of a stabilization and decline of the global temperature. And hopefully we'll be able to stay within the sweet spot. I mean, it's important to be able to keep fossil fuels in the ground, because who knows when next we're going to need to release CO2 to prevent the next glacial from arriving, right? But if we don't reduce those emissions, we face a radically different world. And I want to show this to you from deep time, going back now tens of millions of years into the past. We do know that if you go back 40 to 50 million years ago, the CO2 concentration in the atmosphere was way higher than it is now, 1,000 ppm, maybe more, double, almost triple what it is now. And but the issue is that this was an incredibly much different world. It was a world dominated by forests, woody plants, all the trees of the world, which are currently benefiting from rising CO2 because they have a much greater carbon demand than herbaceous plants, grasses, dominated this world. And if you think that some of the projections for CO2 that may still be on the table include about a 700 part per million by 2100, then you're literally moving you're moving the biosphere back about 30 million years in the space of a century, which is like moving ecosystems backwards in time, at the speed of light, which gives you some sense of the craziness that remains in the world. The kind of risk of pushing us back that far in time over a century or two is just is sheer lunacy in terms of ecological response. So yeah, that's my story, and I hope that you found that interesting, and I'll end there and open up for questions. Thanks, Francesco, for hosting me, giving me the time.
Yeah, Guy, thank you very much. It was indeed a fascinating story.